didn't have to cut me off. Think that I can never thought we were nothing. I don't even need your love. You treat me like a stranger and I feel so loved.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Nur Badri Shah bin Syari. I play the role as a leader for this mini project by Group 3. So our mini project is about Smart Insole. So let's check out the first slide. So the first thing that I would like to present is about the project overview. The title for our mini project is Smart Insole to measure the gait analysis. The purpose of this project is to measure foot pressure and analysis walking pattern of a normal human, or we can call it as a gait analysis. The idea behind of this project is we would like to use the flexible insole sensor such as FSR or piezoelectric to monitor walking phase. The problem that we found with this project is the traditional gait analysis system are very expensive and lab based. It cannot be run by a normal human or outside of the lab. So we bring out the solution to develop a low cost, portable and real-time insole system. The application for this mini project can be good and useful for rehabilitation, sports, training and health monitoring.
From previous study by researchers discovered that a single sensor such as accelerometer could detect posture. However, they often encountered accuracy issues caused by noises and limited motion data. In the past, gait or posture analysis mainly relied on traditional systems. This system used external motion capture cameras, reflective markers, and force platforms. Basically, sensors were placed around the person or on their body, and multiple cameras tracked their movement. This method gave very precise data, but it also had many limitations. It required a lab environment, expensive equipment, and complex setup. Moreover, the system couldn't be easily used in daily life. It was more suitable for research labs or hospital. However, nowadays, research studies have demonstrated that combining multiple sensors significantly enhance classification accuracy. This sensor can collect data in real time as a person walks naturally, even outside the lab. By combining multiple sensors, this method improves accuracy and reduces problems like noise or limited motion data that single sensor often face. It's also cheaper, portable, and more practical for continuous monitoring or rehabilitation purpose. Okay.
Okay, so next for methodology, system setup. Sensor placement, FSR sensor array is positioned under the foot to capture ground reaction pressure. LM35 or temperature sensor detect temperature variation linked to physical contact or inactivity. Data acquisition or processing. Sensor signal are sent to the DAC system which is interfaced with LabVIEW. In LabVIEW, the signal are processed through threshold logic and pattern analysis to determine posture. For classification logic, pressure plus pressure equal to posture classification. First, we got the FSR sensor array placed under the foot. The sensor detects the ground reaction pressure. So when you're standing, walking, or sitting, the pressure pattern change, and that's what the sensor captures. Next, there's the LM35 temperature sensor, which means measure temperature change. This help detect whether the foot is active or inactive, because when you are not moving for a while, the surface temperature might slightly change. Next, all the signal from the sensor are sent to the DAG system, which acts as the bridge between the sensor and LabVIEW. In LabVIEW, the signal are processed using threshold logic and pattern analysis. From there, the system can classify the posture, for example, whether the user is standing, sitting, walking, or resting. So in short, this setup combine pressure data from the FSR sensor and temperature data from the LM35 process it in the view and then determines the user posture automatically.
So now I'll be explaining about the block diagram for our project. So our system is designed to monitor and analyze a person activity, specifically walking, running, and sitting by measuring both foot pressure and temperature. This helps detect abnormalities or discomfort that may indicate injury or fatigue. While we will start with the input section, the Insole has two sensors, an FSR sensor, which detect foot pressure, and LM35 sensor, which measure foot temperature. So these two are embedded in the Insole to capture real-time data during walking, running, and sitting. The signal go into the signal conditioning circuit, which ensure the reading are clean and within the correct range for ESP32 microcontroller. So the ESP32 process the data to detect activities type and gait phases such as heel strike, mid stance, and toe off during walking and running. For sitting, it monitor pressure distribution and temperature to ensure the comfort. So after processing, the ESP32 send the data via Wi-Fi to the mobile or PC application built with Blink, where user can see real-time time graph versus time for both pressure and temperature. For both pressure and temperature. So the data is also uploaded to the cloud for storage and analysis, allowing long-term monitoring and performance review. So finally, there is a feedback control, which is here. If abnormal gait pattern, running stress, or pressure issue while steering are detected, an alert or adjustment signal is sent back to the microcontroller. This makes the system a closed loop continuously monitoring and improving the user's comfort and safety. So in summary, the Smart Insole for gait analysis provide a complete solution for walking, running, and sitting, from sensing and processing to wirelessly monitoring and feedback. It make the activities monitoring more efficient and user-friendly. So that's it from me. Thank you.
For equipment overview, we use two main sensors, the Force Sensitive Resistor FSR and the LM35 temperature sensor. These two sensors work together to detect and classify human postures such as standing, walking, or resting based on pressure and temperature data. First, the FSR sensor. The force sensitive resistor is placed under the foot to measure the pressure distribution when a person moves or stands. When pressure is applied on the sensor, its resistance change. This change is resistance is converted into a voltage signal which is then read by the SP32 microcontroller. From the signal, we can analyze different pressure patterns. For example, high pressure while standing or varying pressure when walking. We use the FSR because it is cheap, reliable, and provides accurate pressure readings, which makes it very useful for detecting human motion. Next, the LM35 temperature sensor. This sensor is used to measure the body or environmental temperature change during activity. The LM35 outputs an analog voltage that increases by 10 millivolts for every 1 Celsius rise in temperature. We use it because it is sensitive and accurate enough to detect small temperature variation, which can help identify if a person is active or resting. Both sensors send their analog data to the SP32, which process the signals and send them to LabVIEW. In LabVIEW, the data is analyzed and displayed as real-time graph, and the system classifies the posture as walking, standing, or either. So in summary, we use the FSR sensor to detect pressure pattern and the LM35 sensor to measure temperature change because both are low cost, accurate, and easy to integrate into our posture classification system. Thank you.
My name is Muhammad Chris and I will present about the results. In this slide, we can see the result of our system. Pressure sensor or FSR were placed under a different region of the foot to record force changes during walking. The collected data was sent to a microcontroller and displayed or logged on a computer or mobile app. From the data, we plot a graph of pressure versus time. As shown on the right, there are two clear peaks. The first peaks represent heel strike when the heel touch the ground, and the second peak represent toe off phase when the foot push off. Between these two peaks is the mid-stand phase, where body weight is balanced on the foot. By comparing left and right foot reading, the system can detect imbalance or abnormal gait patterns. This information is useful for analyzing walking behavior, help calculate step counts, walking speed, and pressure distribution. At the bottom, we have the example showing how pressure and temperature relate to activity. High pressure with stable temperature indicates standing. Fluctuating pressure with temperature change indicate walking. Low pressure and minimal temperature variation indicate rest. Overall, the system actively distinguishes between walking, standing, and resting states, while also identifying different gait patterns using both pressure and temperature data. That's all from me.
Hello, my name is Muhammad Safwan bin Halim. For conclusion, the system can grade and analyze normal human gain pattern accurately. The collected data can be accepted as a reference for medical students on walking behaving. This helping is defining abnormal gain or balance issues in painted is good to respond rehabilitation and physiotherapy monitoring. This study helped to demonstrate how a low-cost wearable insurance can contribute to medical research and clinical analysis. This brings us to the new level of innovation such as exoskeleton processing.